Hello. In the previous video, we talked about the adjoint of a matrix. So in this video, we will prove a theorem. It says, let A is n by n matrix. So for n by n matrix, we say that A belongs to R to the power n by n. It means A is an element of the set such that the set consists of n by n matrices whose entries are real numbers, okay? So that means A is one of those matrices. So there are matrices which are n by n matrices whose entries are real numbers. A is one of them, okay? So it says if A is n by n matrix, then A times adjoint of A is equal to determinant of A times identity matrix of order n by n. This is the theorem. Okay, we will prove this theorem. In order to prove the theorem, we will consider arbitrary n by n matrix A, and then we multiply A with adjoint of A. Okay, so since n can be any number, so we will prove this theorem for particularly for n is equal to 3. Okay, so if n is equal to 3, my matrix is 3 by 3. So I will take 3 by 3 to make my calculations easy and simple. Okay, so we consider A is equal to this matrix, and if A is this matrix, then we can find the adjoint of A. And in the previous video, we have considered, actually we have asserted that the adjoint of A is obtained by writing cofactors A11, A12, A13 up to so on, A21, A22, A23 and A31, A32 and A33 and its transpose. Okay, so if A is this matrix, then its adjoint is this one. So what we have to do, we have to prove A times adjoint is this is equal to the product of the determinant with identity matrix. So in order to prove this, I will take this and do some calculations and try to make this thing. Okay, so I will consider the left hand side and prove the right hand side. This is the way how we prove the equation. Okay, so left hand side is, whenever you have to prove an equation, you consider the left hand side and you make the right hand side. Okay, so left hand side is A times adjoint of A. If I put their values here, in place of A, we will put its value, and in place of adjoint of A, we will put its value. Since here we have transpose, so first I will apply this transpose and then we multiply. Okay, so what we have done, I have written A as it is, and since I have to apply this transpose on it, that means this row will become the first matrix and the second row will become the second column, A21, A22, A23, and similarly the last row will become the last column, A31, A32 and A33. Now transpose is applied, so therefore I have not written transpose now. Now I will multiply both matrices. Look how we multiply. First of all, I will multiply this row with this column. I will get A11, A11, A12, A12, okay? I will have A11, A11, A12, A12, A13 and A13, okay? Then I multiply this with this thing. I have A11, big A21, A12, A22, A13, A23, okay? So I have A11, A21, A12, A22, A13, A23. And then I multiply this with the last column. So if I multiply this with the last column, so A11, A31, A12, A32, A13, A33, okay? So I will write A11, A31 plus A12, A32 plus A13, A33, okay? Now I will multiply the second row with the first column. So it is A21, A11, A22, A12, A23, A13. Okay, so I'll multiply these things. So I have written A21, A11, A22, A12, A23, A13. Now I will multiply this row with this thing. It is A21, A21, A22, A22, A23, A23. Okay, I will write this thing. So I have written down this thing. Now I multiply this row with the last row. So I have A21, A31, A22, A32, A23, A33. So I will write this whole thing here. So I have written down this thing here. Okay. Now we multiply the last row with this and then this and then this. After multiplying the last row in the similar pattern, we will get, so we get this row. Okay. Now this is actually left hand side, which is A times adjoint of A. Okay. Now if we look at this product, we have two kinds of numbers. Look at this, these three values. Here you will check the indices are same. A11, A11, A12, A12, A13, A13. Here the indices are same. So also the indices here are same. A21, A21, A22, A22, A23, A23. Also here both are A31 and both are A32, both are A33. Okay. In these, I mean diagonal entry, these are the diagonal entries, because here the pivot entry is this one, here the pivot entry is this one, here the pivot entry is this one. So these are three diagonal entries. If you look at the non-diagonal entries, for example, if you look at the entries other than these, if you look at the entries other than these, the indices here are not same. You can check. For example, here you have A11, here you have A12, so the indices are different. A21, A22, so they are different again. A13, A23, so they are different. Also, you can check here the indices are different, here the indices are different, here the indices are different, here they are different, here they are different. Only the same indices are in the diagonal. Okay. When the indices are same, what does that mean? Okay. For example, if I look at this number, this is the determinant of A. This number is the determinant of A. How? Look. Here is the matrix A. If I expand the determinant along this row, okay, I will have A11 and the cofactor determined by this entry, right? which will be A11. Similarly, then I will have this number A12 and the cofactor determined by this number, which is A11, A21. And then I will write this number A13 and the cofactor determined by A13, which is A13. So if the indices are same, then this summation is actually the determinant of the matrix. So this is the determinant of A. Okay, so this is happened when we expand the determinant along the first row. If we expand the determinant along the second row, we will get this number. Okay, if we expand the determinant along the last row, we will get this number. So that means they are all determinants of A. So in place of these, I can write the determinant of A again, determinant of A, here also determinant of A. The question is, what are these numbers then? Since here the indices are different and we have a theorem which is not proved in this book, if the indices are different, then this sum is always 0. This is the theorem, but it is not proved here. We will use this theorem here. We will not prove because this is not the title of the book. Okay, so these numbers, since the indices are different, so these numbers are 0. These sums are 0. So here everywhere else is 0. Here you have 0, here you have 0, here you have 0, here 0, here 0, and here 0. Okay. Now look, in the whole matrix, the determinant of A is common and the other entries are 0. So I can take determinant of A outside. And inside I have, because it is determinant of A times 1, determinant of A times 1, determinant of A times 1, okay? So I can write here 1, 0, 0, 0, 1, 0, 0, 0, and 1. What is this? Determinant of A times identity matrix of order 3. Look, what we had to prove, we had taken the left hand side and we proved the right hand side. Okay, in this theorem the left hand side was this and the right hand side was this. So whenever you take the left hand side and performing some operations on the left hand side, if you are able to make the right hand side, then we say that these two things are equal. We say the left hand side and the right hand sides are equal. Therefore, our claim is proved. Okay, so this theorem is proved. Hence, so I will write hence proved. Okay, since this is proved for 3 by 3 matrix, using the same argument but with more calculations, we can write bigger matrix for 4 by 4, 5 by 5, 10 by 10 matrix. We can use similar kind of calculations and we will get the similar bigger matrix. At the end, we will get the diagonal entries determinant and the off diagonal entries we will get 0. Okay, so this theorem is proved generally for all values of n. Okay, so we can say that for every n, adjoint of A times matrix A is equal to determinant of A times identity matrix of order n. Okay. Or in other words, you can write A times adjoint of A is equal to, this we have proved, A times adjoint of A is equal to this thing. Okay. Now, if we multiply both sides by A inverse, I mean, if I multiply here by A inverse and here by A inverse also, this A and A inverse will get cancelled. You will get only adjoint of A here. Okay? And here you have A inverse times, since determinant of A is a number, so I can write determinant of A first. Then A inverse times identity matrix. Okay? A inverse times identity matrix. Since there is a property, if a matrix multiplied by identity matrix, we will get no change. Identity matrix is a matrix. If you multiply identity with any matrix, you will get that matrix, okay? So that means the product of these two things is only A inverse, okay? Okay, so if the determinant of A is not equal to 0, then we can divide both sides by determinant of A. If we divide by both sides by determinant of A here and here, this will cancel, and here you will get A inverse. So I will have A inverse equals adjoint of A over determinant of A. Okay, so this is the way how we find the inverse of a matrix.